let's learn how to factor trinomials when a does not equal 1. As discussed in a previous video, when factoring trinomials, we must consider two cases. In this video, we're going to consider the case when a is not 1. This is a slightly more difficult case, and we like to use helping methods such as the AC method or the Kung Fu method. In this video, I am going to show you how to use the AC method. For the easier case, when a equals 1, we can use a strategy where we find two numbers that multiply to equal the last and add to equal the middle, but that does not work for the a not equal to 1 case. Let's see how the AC method works to help us. There's lots of different methods you can use for this case, but for this video we're going to focus on the AC method. Here's the steps for the AC method. Remember, we would only use this method if a is not equal to 1. If a is equal to 1, it's the easier case that's discussed in a previous video. Let's do an example. In this example, we're asked to factor this polynomial. Remember the factoring flowchart? Before we start any factoring problem, we must factor out the GCF. In this case, the GCF is 1, so we can proceed. The next step of the factoring flowchart is to determine how many terms your polynomial has. Ours has 3 terms, thus it's a trinomial. But we're in the case where a does not equal 1, as we see the leading coefficient is 21. Thus, we will use the AC method to factor. Let's use the steps for the AC method. First, we must check for GCF, but we already did that. Second, we multiply a times c, which is 210. Next, we must find two numbers that multiply to equal 210 and add to equal the middle term, negative 41. This is similar to what you do with the a not equal to 1 case for trinomials, except we're not trying to find numbers that multiply to equal 10. Instead, we're trying to find numbers that multiply to equal a times c, which is 210. So we need to find two numbers that multiply to 210 and add to equal negative 41. Remember the sign analysis. Since 210 is positive, and the numbers must add to a negative, both numbers must be negative. The sign analysis is displayed in this chart, and it's discussed in more detail in a previous video. Let's find negative factors of 210. The first option is negative 1 and negative 210, which add to negative 211, which is not negative 41, so these factors do not work. Let's find the next pair of factors. Negative 2, negative 105. These add to negative 107, so they do not work. The next pair of factors is negative 3 and negative 70, but they don't work. The next pair of factors don't work either, as they add to negative 47. The next pair of factors works, as they add to negative 41. So we found the two numbers that will work. There's more factors of 210, but once you find the factors that will work, you can stop. So you may have to search for a little while before you find the factors that work. This completes step 3. Now we move on to step 4. If this was the easier case of trinomial factoring when a equaled 1, we would basically be done. Our factorization would just be these two numbers with the variables. But this is the more difficult case. We're not done. We move on to step 4. The next step is to expand this middle term into these two numbers added together. Because negative 6 plus negative 35 equals negative 41, we can rewrite the middle term as negative 6x plus negative 35x. So step 4 of the AC method is to expand the polynomial into these two terms. This is still exactly the same polynomial because negative 41x is the same thing as negative 6x minus 35x. It's just in a slightly different form. Now let's factor this polynomial. How many terms does this polynomial have? 4. How do we factor 4-term polynomials? Factoring by grouping. This method was discussed in a previous video. If you need help with that method, please refer to the previous video. So step 5 of the AC method is use factor by grouping to factor the 4-term polynomial created by expanding that middle term. We factor by grouping first by separating the 4 terms into 2 pairs of terms. Then, factor out the GCF from each of those pairs. Notice how I made the GCF for the orange pair negative since the leading term of that pair was negative. Factoring the GCF from the green pair gives this. Factoring the GCF from the orange pair gives this. What's in between? A plus. That's very important. Otherwise, it may look like you're multiplying, but you're not. You're adding these two together. However, in this case, since we have plus minus, we can simplify by just writing minus. Is this factored? No. We have two algebraic expressions separated by a minus sign. Thus, it's not factored. What's next? We have 2 terms. Let's factor the GCF from these 2 terms. Notice that each term has a 7x minus 2 in common. That's the GCF of these 2 terms. Factoring out the GCF produces this. If you need help factoring the GCF, please refer to the previous video on that topic. Is this in factored form? Yes, as it's the product of 2 algebraic expressions. So we're done. We found the factorization of this polynomial. Thus, we found our answer. However, we should always check our answer by multiplying to see if it equals the original polynomial. Multiplying produces this polynomial. Does this equal the original? Yes. Therefore, our factorization is correct. Notice that negative 2 plus negative 5 does not equal the middle term. That's because we're in this case when a is not equal to 1. You cannot use that strategy in this case. Instead, we had to use a helping method, like the AC method. Let's look at another example. We're asked to factor a polynomial. Before we do anything, we must check for a GCF. The GCF is 2. We factor it out, resulting in this polynomial. This polynomial is factored, as is the product of this algebraic expression with this algebraic expression. However, it's not completely factored. We must check and see if we can factor the inside polynomial. Let's focus on just this inside polynomial for now. Once we find its factorization, we can go back to here to get our final answer. Looking at just this polynomial, we have to decide how many terms it has. It has 3 terms. Thus, it's a trinomial, and the leading coefficient is not 1. So we cannot use the strategy where we find 2 numbers that add to equal the middle and multiply to equal the last. Instead, we can use a helping method, such as the AC method. The first step is to multiply a times c, which gives us 100. Next, we must find factors of 100 that add to equal the middle coefficient, 20. Next, let's do a sign analysis. Since 100 is positive, both numbers must be the same. Since they must add to a positive number, both numbers must be positive. The first factor pair is 1 and 100, but they don't work as they add to 101, not 20. The next factor pair also does not work. The next factor pair also does not work. The next factor pair also does not work. The next factor pair works as they add together to equal 20. So 10 and 10 are the numbers we need. The next step is to expand the middle term into 10y plus 10y. This polynomial is still equivalent, as 10y plus 10y still equals 20y, but it's in a different format. Now we focus on factoring this polynomial. This is a 4-term polynomial, so we must use factor by grouping. We split the 4 terms into 2 pairs, and factor the GCF from each pair. Then, we see our 2-term polynomial has a GCF of 5y plus 2. Factor that out, and we get this. This is in factored form. Notice how the two binomials are the same. Thus, we can use the definition of exponents to simplify. This is repeated multiplication of the base twice. Therefore, we can write this more simply as 5y plus 2 squared. Thus, we factored the inside polynomial. We can now replace this with its factored form. Thus, we arrive at the factorization for the entire polynomial. And we have our answer. As always, we should check our answer by multiplying. To multiply this, first you have to remember to use the definition of exponents and write as repeated multiplication. Next, we use the full procedure to get this. Finally, we distribute the 2 to get this. Does that equal our original polynomial? Yes. Therefore, our factorization is correct. Let's do one more example. Before we start, we must check for GCF. GCF is 1, so we can proceed. This is a trinomial where a is not equal to 1, thus we will use the AC method. A times c is 18. Let's find factors of 18. They must both be negative since they need to add to negative 7. Here's our first factor pair. It does not work as it does not add to negative 7. The next factor pair also doesn't work. Neither does the next factor pair. And that's all the possible factor pairs of 18. Thus, the polynomial is not factorable. This should not surprise you, as many polynomials are not factorable. We can write for our answer, the polynomial is prime. In this video, we learned how to factor trinomials where a was not equal to 1.